Good afternoon, Professor Sarnak, Professor Han, distinguished guests, esteemed colleagues, and all honored participants. It's my great pleasure to welcome you to the Shaw Prize Lecture in Mathematical Sciences 2024, titled Primes and Patterns in Number Theory and Geometry. I'm Professor Ngai Mok, Chair Professor of the Department of Mathematics at the University of Hong Kong. We are very honored to welcome Professor Peter Sarnak today, esteemed laureate of the Shaw Prize in Mathematical Sciences 2024. His contributions to number theory and analysis have profoundly influenced applications that resonate throughout the digital world. The Shaw Prize, established under the auspices of the Sir Run Shaw in 2002, is an international award dedicated to honoring individuals who are actively engaged in their fields and have recently made significant advances. This award aims to promote societal progress, enhance quality of life, and enrich humanity's cultural heritage. Today, we gather to celebrate the spirit of excellence and its profound impact on the world. And to move forward, I would like to invite Professor Guangyue Han, Interim Head of the Department of Mathematics at the University of Hong Kong, to deliver the opening speech. Professor Han, please take the stage.
Professor Sarnak, Professor Mok, Professor Zhou, esteemed colleagues and students. Good afternoon, and welcome to the Shaw Prize Lecture in Mathematical Science 2024. I'm Professor Guangyue Han, Interim Head of Department of Mathematics at the University of Hong Kong. It's a great honor to stand before you today as we celebrate not only the remarkable achievements within our field, but also the collective journey of mathematical exploration. Mathematics is a discipline where tradition meets innovation, continuously evolving and expanding its influence beyond academia. It plays a pivotal role in shaping the digital age, driving the advancement in science and technology, and addressing some of the most complex global challenges we face today. From breakthroughs in data science to innovations in healthcare and environmental sustainability, mathematics is at the forefront of discovery and progress. At Hong Kong U, we envision our department as a vibrant hub of creativity and excellence. We're deeply committed to nurturing an environment where curiosity thrives and new ideas flourish. By fostering interdisciplinary research, encouraging collaborations across various fields, actively engaging with communities through outreach programs and public lectures, we position ourselves as leaders in mathematical innovation. Our goal is to make mathematics accessible and exciting for everyone, inspiring the next generation of mathematicians, showcasing the beauty and relevance of our discipline. So today, we're privileged to be joined by Professor Peter Sarnak, the 2024 Shaw Prize laureate in mathematical sciences. His contributions to number theory analysis exemplify the beauty, complexity, and interdisciplinary nature of mathematics. Professor Sarnak's work not only deepens our understanding of these intricate fields, but also resonates across the digital world, influencing a broad spectrum of applications. So as we embark on this journey of learning and discovery together, I encourage each of you to embrace the opportunities ahead. Let us build upon the legacy of those before us, contribute meaningfully to the ever-growing body of mathematical knowledge. Through collaborations and the exchange of insights, we can tackle complex problems more effectively and create a vibrant research network. So today we are filled with hope and enthusiasm as we look to the future. Mathematics is not just a tool for solving problems, it's also a source of wonder and joy. So I want to thank you for your unwavering dedication and passion. So it is your commitment that fuels our collective journey of learning and discovery. So together, let us explore new frontiers, make meaningful contributions to society, and strive for excellence in shaping the future of mathematics. Thank you.
So thank you, Professor Han, for your insightful overview of mathematics. Before we welcome Professor Sarnak to deliver his esteemed lecture, I would like to take a moment to briefly outline his remarkable academic journey. Professor Peter Sarnak is the Eugene Higgins Professor of Mathematics at Princeton University and a Professor Emeritus at the School of Mathematics in the Institute for Advanced Study. He is internationally recognized as one of the foremost analytic number theorists of his generation. Sarnak's academic journey began at the University of Witwatersrand in South Africa, where he initially pursued physics. He then moved to Stanford University in the United States to complete his PhD under the supervision of the renowned mathematician Paul Cohen. It was there that Sarnak's mathematical intuition flourished, leading him to explore topics from number theory to analysis of manifolds. In 1988, alongside Alex Lubotsky and Ralph Phillips, Sarnak introduced the fascinating concept of Ramanujan graphs, now a cornerstone of theoretical computer science. These optimal expanders of theoretical computer science have had far-reaching implications in fields ranging from differential geometry to algebraic groups, offering deterministic methods where randomness had previously prevailed. Throughout his career, Professor Sarnak has received numerous prestigious awards, including the Portia Prize, the Ostrovsky Prize, the Wolf Prize, the Shaw Prize, and many others. His work has been recognized not only for its depth and originality, but also for its ability to connect seemingly disparate areas of mathematics, revealing underlying symmetries and structures. Beyond his research, Sarnak is an exceptional educator and mentor. His ability to communicate complex ideas has inspired countless students, earning him the Phi Beta Kappa Teaching Award at Princeton University. His influence continues to shape the future of mathematics through his mentorship and leadership. I was personally amazed by his dynamism and leadership as a graduate student at Stanford, where we overlapped in our graduate studies. Today, Professor Sarnak will delve into the fascinating world of prime numbers, those enigmatic building blocks of number theory, and the digital realm. Despite their fundamental role, many simple yet long-standing questions about prime numbers remain unanswered. In this lecture, Professor Sarnak will explore these mysteries and the powerful tools developed to address them, particularly the robust sieve method applied to geometric configurations. So, without further ado, it gives me great pleasure to welcome Professor Peter Sarnak to deliver the Shaw lecture.
Yep. Thank you very much for the very kind and detailed introduction. And it's true, we were graduate students together, and it was a great time then. And it's great to see you again, Naomi. I really appreciate being here. I was an honor to give this lecture today. I think I gave some lectures here in 2001, and it's great to be back at Hong Kong University and to be here to receive a very generous prize. Thank you. So I would like to explain the title. The lecture will be, I hope, understandable, at least for the first half or so, by high school and undergraduates. At the end, I might go a little fast, just because I want to state a theorem. All right, so let me explain what we will be talking about. Let me make sure I understand. Okay, good. So I'll be able to move around. This is very good. So a prime number, I was arguing with one of the physics winners of the Shaw Prize. Why is number 1 not prime? This is a very good question, and it's algebraically best explained. But I'll just declare that the first prime is 2, not 1. And they are numbers that are divisible by only themselves and 1. And it's very easy to find them if you just start looking for them. So these are the first 100 primes, 2, 3, 5, and so on. And it's a remarkable, one of the very first theorems ever proved in mathematics, by contradiction, in fact, a theorem of Euclid, that there is no biggest prime. The list continues on forever. That takes proof. It's not obvious by any means. And you change the problem slightly, and we already have stated, I'll state for you in a second, an unsolved problem. One of the great attractions of number theory is it's very easy to state problems that are compelling. It's very easy to state many problems. Most problems that you might state are actually probably undecidable anyway. So how mathematicians choose problems is a very important issue. But I remember myself when I first learned what primes were, you can't not notice that there are primes that differ by 2. They can't differ by 1, because if A is a number and A plus 1 is another number, then one of them must be even, and so it'll be divisible by 2, so only 2 would be allowed. But beyond that, the next gap you could arrange would be 2, and you see these twin primes, and mankind does not know whether this continues forever. Maybe there's a biggest pair of twin primes. That's an unsolved problem. Solving it would not change the world. It's curiosity here. Some problems are driven by curiosity. Some are driven by the obvious, once we have a theory, importance in keeping up the theory and developing in what's true and what's not true. Often the methods are more important, and here there will be some methods I'll explain in a second. All right, so we don't know if they're infinitely many. The strong expectation is yes. I was preparing this in Princeton, and I was driving, and on NPR I heard the news that the biggest prime known was only discovered a month ago. Now, there are infinitely many primes, but the issue is the biggest prime recorded. You might think, well, that's easy, just go and check. And it is true that it doesn't take so long to check whether a number's prime. It's polynomial, as we know today. But to actually write down a very big number and show that it's prime takes some effort. And this is the biggest prime known, which is a rather big number. It's a Mersenne prime. It's the biggest prime number that's been recorded. But we are interested in the theory here. There are infinitely many. And we don't know if there are infinitely many twin primes. So I want to explain what the sieve is, because the sieve is central to this talk. And the reason we call it a sieve, there's a sieve of Eratosthenes that goes back to the Greeks. If you want to make a table of primes, first thing you could do is, the first number 2 is a prime. We see it. And then we strike out all the multiples of 2. And we see what's left, 3. And that's the next prime. And then we strike out all the multiples of 3. Notice when I strike out the multiples of 3, I'm now striking out 6 twice. So if I want to do some kind of counting, I'm going to have to do an inclusion-exclusion process, which can be extremely delicate, and that's what the sieve methods are about, how to overcome that difficulty. Anyway, we continue. The next number that we haven't seen is 5. So 5 is a prime. We strike out the multiples of 5, and so on. I went up to 30 here. We only have to go up to 7, and the guys that we haven't struck out, 11, 13, 17, 19, 23, and 29, are prime. That's because if AB is, if a number is a product A times B, and if A is less than or equal to B, then A must be less than or equal to the square root of the number. And so that's why I don't have to worry about the others. And this is a way of making a table. And this is the Eratosthenes sieve, and you get the primes. The reason it's called a sieve, I hope, is clear, because it's the numbers that remain as you do if you were sieving. Some people call sieve, I call it a sieve. All right, so sieve methods are concerned about trying to produce or count how many primes there are, or something like primes. So how many are remained after this process, and in doing so, we have this very delicate inclusion-exclusion if we want to count effectively. The founder of the theory of the sieve is Viggo Brunn. In a famous paper in 1915, he developed an elaborate way to count. I'll tell you what he used, what he was able to do with it in a second. But I want to point out immediately the most basic thing that he's using, and that we will be trying to generalize to more geometric settings, is the following very easy fact. That when I start striking out numbers, I will want to count. So Z means integers. We always will be talking about whole numbers. So Z are the whole numbers. We can allow negative numbers. Let's not worry about that too much. And suppose I take an integer Q, which is greater than or equal to 1, and I want to count all the integers which give remainder A when divided by Q. That's what this notation means. X congruent to A modulo Q means X gives remainder A when I divide by Q. So I might be looking at numbers which are congruent to 1 modulo 12. And I ask, how many numbers are there less than T, some very big number T, which give remainder A when divided by Q? So it's clear that the number of intervals that you would have is T over Q. That's not going to be exact because T is just some real number. Q may not go into T. But the error is at most 1 because I have an overlap with at most 1. Either I have a guy there or I don't have a guy there. So the principle of what I'm trying to point out here is if I want to count the number of numbers in an arithmetic progression, I can do so rather accurately. T and Q are any size, the error is at most 1. And this is a basic principle in any kind of sieve that Brunn is doing. And this is going to already be a great difficulty the minute I get into any more elaborate or subtle geometric setting. All right, so let me tell you what Brunn proved with this. I won't go into the proof. It's not appropriate here, but I want to tell you what he did and what we know. So I will take a more general problem, not just trying to count twin primes, but let's take a polynomial, f of x, which is a polynomial expression. Everything's integers. The coefficients are integers. And I want to ask, for how many x's, or which x's, is f of x prime, or something that I'll call almost prime, which I'm going to define in a second. So instead of asking just for twin primes, we will ask a very general problem, and this was asked very quickly, and this is what Brunn fundamental theorem is about. So the Brunn fundamental theorem, which is based on his sieve, I will add the word saturation. That's what we called it when I get to the work that at the very end. I like the term saturation because it's a notion that when you go to several variables, which we will very quickly, is very important. So we've got our polynomial, and this is his theorem, that if you give me any polynomial, there is a number. So there's a number R, which depends on F, and you can work out the dependence. So if you give me F, I will be able to write down what R is. The number's finite. I will explain what this means in a second in concrete terms, such that the integers x at which f of x has at most r prime factors is infinite. So let me repeat that. F is any polynomial. I'm giving up my goal is reduced to not showing that f of x is prime, which I would like to show if it were true, like with the twin prime, but f of x has at most r prime factors. So that's an approximation to being a prime, and an almost prime is a number which has got a fixed number of prime factors, which is at most some fixed number. I'll give an example, then it'll become, I think, even clearer what I'm saying here. So the smallest number for which there are still infinitely many x, for which f of x has at most r prime factors, I will call the saturation number of the polynomial. So Brun's theorem says that R is always finite from his process. I'm just telling you the result of what he could do. Let's apply this to the polynomial x into x plus 2. That's a good polynomial. And in that case, he says there's a number R such that the number x times x plus 2 infinitely often, x times x plus 2, has at most R prime factors. That's a very big first step towards the twin prime conjecture. The twin prime conjecture would say that x is prime and x plus 2 is prime, which would mean that the saturation number of x times x plus 2 is exactly 2. That is, you're making x prime and x plus 2 prime infinitely often. Remember, the twin prime is a question about there being infinitely many x where x and x plus 2 are prime. So the reason that this is a nice way to formulate this is, while we don't know the proof, we don't know how to prove the twin prime conjecture, we certainly believe it's true, the best result towards the twin prime conjecture is due to, it's J.R. Chen, not just R. Chen. I'm missing J over here, I apologize. Who proved in 1973 under quite difficult conditions during the Cultural Revolution, competing with the European people developing the sieve, the fine structures of the sieve, and Americans. He was able to do better than all of them, and he came as close as you can to proving the twin prime conjecture without proving it. That is, he proved R is less than or equal to 3. So he's saying that there are infinitely many numbers x, so that x is prime and x plus 2 is a product of at most 2 primes. So the saturation number is less than or equal to 3. Before him, Pan had 5 or something. People were getting that number down. Brun just proved it's finite. Then the number was brought down, hoping to get down to 2. There's a good reason that those methods cannot give 2. That's why we stuck. But he came down to 3, and 3 is as close as you can get to 2 without proving the full thing. That's the best thing we know towards twin prime, and it's a remarkable theorem. And it's Brun's sieve applied much more in a much more sophisticated and elaborate way with switching of sieves. So that's the Brun sieve, and I'm going to get now to much more concrete problems in a second, in case you're worried, but I wanted to state a few theorems of what we do know. So Brun tells you that this number is always finite, and then the question of determining the number is extremely difficult, because that's like solving twin prime. But we can look for such theorems where we do know the exact answer, and there are a few. So firstly, Euler conjectured that there are infinitely many x's for which x squared plus 1 is prime. There's no obvious reason why x squared plus 1 should not be prime because of some divisibility, but that's just as wide open, and in fact more wide open than the twin prime. So the saturation number for that, that's a polynomial, is at most, is it me or is it, maybe it's those, yeah. The saturation number for x squared plus 1 should be 1 if there are infinitely many prime x's for which x squared plus 1 is prime. Ivanich in 78 did the analog of what Chen did for x squared plus 1. I've got a loud voice. Let's put this off. Is that okay? Can I put it off? No, I've got a loud voice.
You sure?
Yeah. Okay. Can you hear me at the back? Okay. So this is much better. So Ivanich proved that the x squared plus 1 is the infinitely many x's. The infinitely many x's for which x squared plus 1 is either prime or a product of at most 2 primes. So the saturation number of x squared plus 1 is at most 2. The conjecture is it's 1. So as I say, determining the exact answer is usually extremely difficult. But I want to give you some examples where we do know the answer. So are there infinitely many x's where x is prime? Yes, that's Euclid's theorem. So for the polynomial x, R is 1. That's Euclid. One of the great theorems that I always teach, every course I teach, I always first prove this theorem. I don't even care what the course is. This is such a great theorem. It invented characters, it invented harmonic analysis, it invented series, L functions, non-vanishing. So I just walk in, and that's, first lecture is always this. It brings everybody back. And then I say, what's the course? And that's this theorem here, that if you take the polynomial ax plus b, then you may have a problem. Suppose this was 2x plus 2, then you would always be even. So as long as there isn't some silly congruence divisibility obstruction, and that condition is that a and b have no common factor, the GCD of a and b is 1, then there are infinitely many primes in arithmetic progression. Still my favorite theorem in math. So each time you determine the saturation number, you've done something rather interesting. All right. There is a beautiful theorem by Yitang Zhang, a story some of you might have heard. I don't have time to repeat it here, but he proved an amazing theorem, which also comes close to proving twin prime, except that you have to do something a little different. So why put the number 2? You could ask, you better not put 1. I pointed out that if that were 1, then one of those numbers would be even. But as long as there's no divisibility obstruction, you could make the same conjecture. And of course, mathematicians make that conjecture. And so what he proved is there's at least some h. He can't tell you any h for which he can prove it. But there is an h, which is finite. It's less than a few hundred, for which x times x plus 2, both x and x plus 2 are prime infinitely often. So it's also a remarkable theorem, but he's got to give himself h as a variable. But the remarkable statement is there are infinitely many x for which x times x plus h is both a prime, or the saturation number is what it should be, 2. So these are, I'm giving you some landmark theorems. Where we have more results and where the direction we going is, let's suppose I have more than one variable. So instead of having a polynomial in one variable, I have a polynomial in 2 variables. Then I want to make every definition to be the same as before. So the saturation number is the saturation number would be the smallest number. In defining the saturation number, I'm allowing now 2 variables, x and y, to be integers. And I want f is a polynomial in 2 variables now, to be prime or almost prime. But there's a big difference between 1 variable and 2 variables. In 1 variable, you just say infinite, and everybody's happy. We don't ask for more, except for infinitely many twin primes. But if I'm 2 variables, maybe there'll be infinitely many solutions, but they're not rich in 2 dimensions. So the notion of infinite is not the right one in 2 variables. That's in my opinion, and that's going to change for this reason. And I'm going to illustrate for you some beautiful examples where this is very clear. So I want not to just x1 and x2 to be an infinite set where f of x is prime or r almost prime, but I want them to be rich. And rich means something, and here's a definition which is already sophisticated, but it's very easy to understand. Rich means that the set of x1 and x2 for which this is true, your infinite set, do not satisfy some non-trivial algebraic equation. They don't lie on some curve, which is given by a polynomial. And that notion is to say that you're Zariski dense. So I will use the word rich so that nobody can complain instead of Zariski dense, because that sounds very fancy. But that's all it means, is that I don't want just infinitely many, I ask for more. Very often in math, by asking for more, you can then prove much more, because it's like if you're trying to prove something by induction, and you've got a weak hypothesis, and somebody comes into your ear and says, hey, why don't you try and prove more, prove this, and then the induction goes very easily. Very much a case here that if you ask for Zariski dense, rich, that's the right notion, because various things are maintained under certain transformations. All right, so we want that to be true, and the saturation number is the same, defined the same way. I want not infinitely many x1, x2, such that f of x1, x2 is prime, but infinite as a rich set of x1, x2, where f of x1, x2 is prime. And if we do that, the Brun sieve works identically, and the saturation number is always finite. So this is always going to be finite by Brun's arguments. Brun is a very general, robust argument that these numbers are finite. So the main big step from infinite to finite, he's done for you. But from finite to the minimum number, extremely difficult. Okay, there is one case where we really understand things well, and I'll explain why now in a second. So if f of x1 factors into linear factors, so it's not in one variable over the complex numbers, everything factors into linear factors. That's a fundamental theorem of algebra. But in several variables, this may not happen. So if you do factor into linear factors mean they are a linear function of x1 and x2. So it's ax1 plus bx2 plus c. Everything's integers. So T linear factors, and you could try and make f of x prime. There is an amazing theorem here, and that is that we do understand the saturation number in this case. So if f factors into linear factors, and we have f as a polynomial in at least two variables, then for t less than or equal to 3, if there are three linear factors, this is a famous theorem of Vinogradov. And in general, this is a theorem of Green, Tao, and Ziegler from 2012. And it says that the saturation number is T if there's no local obstructions. There's no reason, no divisibility obstruction. Then you can find a rich set of x1, x2 where each of these separate linear forms is separately prime. That's an amazing theorem. It's very deep. And it's remarkable in that the ideas that go into it. So the proof, Vinogradov used what's called the Hardy-Littlewood circle method. And the remarkable understanding that is due to Furstenberg is that the circle gets replaced by a null manifold. So for mathematicians, this is extremely pleasing. You see what the right notion is replacing the circle. And this null manifold, together with works of ideas of Gowers and Simoretti's theorem and Simoretti's proof, these ideas go into this proof of this remarkable theorem. But you have to have linear factors. Okay, so that's more or less what we know. There are other theorems, of course, that we know, but I've given you a quick summary of what the definition of saturation number is in a few cases where, and most importantly, the Brun sieve. And now I want to give three very concrete geometric examples, and then I'll state the theorem that my colleagues and myself proved. So, and these three examples are very geometric, they're very basic, and I want to compute saturation numbers associated to them. So I think most people know Pythagoras' theorem, and a Pythagorean triple are triangles in which the sides are integer lengths. And you could make them positive if you like. So the simplest Pythagorean triangle is 3, 4, 5. 3 squared plus 4 squared is equal to 5 squared. The set of solutions to x squared plus x1 squared plus x2 squared minus x3 squared equals 0, this is a cone in 3 dimensions. And we're looking at the integer solutions, and we'll assume that the solutions are primitive, no common factor. And there are infinitely many solutions here. And I want to look at the number theory of these solutions. So I'm going to ask a question that I suspect the Greeks asked, and we'll answer, is what's the saturation number of the area? So I want a rich set of Pythagorean triples, rich meaning that they don't lie on satisfy some non-trivial algebraic relation. So I'm going to give you a picture in a second. I want many solutions, and I want f of x, which is the area, the base times the height over 2. It's always divisible by 2. I want the area to have a minimum number of prime factors. So what's the minimum number of prime factors that the area can have and still have many solutions? Okay, so the first question, is the saturation number finite? There will be a very general theorem that gives that that's always finite. That's one of the main big theorems. But what the saturation number is, so assuming people, so I'm now going to do something very basic. So here's what the question is. Here are the Pythagorean triples, triangles, ordered by their area. And you can see I've computed the area. These are ordered, they only, for each, they can be ordered this way. And in each case, I factor the area into its prime factors. So the area is 6, there are 2 prime factors, there's 30, there are 3, and so on. This is the last time you'll ever see 4. There are only these cases, these few cases there, where there are only finitely many Pythagorean triples which have only 4 prime factors. If you look carefully, you'll see that 3 and 2 are everywhere present. There's always a factor 3 and 2, and that comes from just divisibility inspection. The other factors are the interesting ones. And we see that there are examples where there's 6, and if you keep on going, there's some with 5. And if you keep on going, the number of prime factors will want to increase, but we want to see, is it true that there's a risky dense or rich set of Pythagorean triples for which the area has only 6 prime factors or 5 prime factors? So let's look at a picture. This is a picture of the Pythagorean triples on the cone. The blues are what most of the Pythagorean triples are. The reds over here are the ones which have 6 prime factors. And the blues are the ones which have 5. And you can see the blues are lying on a curve. I could write the equation of the curve. They're not rich. But the red ones looks to be rich. They're still fewer in number than most of them, just like twin primes are fewer than most numbers. But there's a good chance that 6 is the answer here. And that's an amazing theorem. The answer is 6. This is a problem about saturation for, I'll explain where it comes from in a second. And the reason this problem, why I'm illustrating this example, a geometric example, is it allows me to explain 2 points of view which are possible in this case, but not possible more generally. So this goes before the Greeks. Turns out that Pythagorean triples can be parameterized by free variables. So the Pythagorean triples satisfy this equation, and there's a little bit of algebraic geometry that was known pre the Greeks how to parameterize these, and let me show you how it's parameterized. So if you have x1, x2, x3, a Pythagorean triple which are relatively prime, then x1 can be written as a squared minus b squared, where a and b are free integers and also relatively prime and not of the same parity, and x2 is 2ab, and x3 is a squared plus b squared. So the fact in x1, x2, x3, they satisfy equation. But now the a and b are any pair of numbers. So I immediately see that there are many solutions this way. I also see the divisibility by 3 and 2 that's also obvious from this. And I can also convert the saturation problem to a question about a and b. This is very special for this example. Another way of looking at the Pythagorean triples, and I'm going to assume that people know what a matrix is, that's the limit of what I'm assuming, is if you take these 3 by 3 matrices that I've written down here, they're not hard to find. It turns out that they have the property that quadratic polynomial, which was x1 squared plus x2 squared minus x3 squared, if I take f evaluated at aj of x, that's the same as f at x. That is a rotation. So in ordinary rotations, you think of x1 squared plus x2 squared plus x3 squared. And then you have the rotation group, all the transformations which preserve the distance to the origin. That's called the rotation group. If you have a quadratic form which is indefinite, x1 squared plus x2 squared minus x3 squared, you can still look for matrices which have that property. And you can take these matrices and multiply them, and they form a group. And this group way of looking at it is the way we're going to discuss this problem from here on out. So it turns out these 3 matrices have this property, and because they have this property, it means that if x1, x2, x3 satisfy the Pythagorean equation, that means they lie on the cone, then so will aj of x, and for each j. And that means that any product of the a's apply to x. So all the matrices that you get by multiplying a1, a2, a3, and you will get a whole group of those, will have the property that all those points that you get, so I'll call gamma the matrices you get by multiplying the a's, that's a group. And I take this group, I apply to 3, 4, 5, our favorite solution, we'll get all the solution. So this is another way of parameterizing all the solutions by action of this transformations of space. And that's a setting in which we're going to try ask these and answer these questions. So there's the ancient way in this example, and there's this way. And from both ways, it's very easy to see. Well, from the second, it's part of this big theorem that the saturation number is finite. But the fact that the saturation number is 6, that is that there is a rich set of Pythagorean triples for which the area is 6 and not more, 6 prime factors, can be seen from the first parameterization. That is, from the first parameterization, which was the a and b, you will get 4 linear forms in 2 variables, and the Green-Tau theorem will give that to you. Green-Tau-Ziegler theorem, my apology. and you can check all the side conditions. So it's a very beautiful, in my view, example of where we know exactly the answer, which is what I'm saying is very rare. You can't do it with 5. You saw that on the picture. It looks like the solutions lie on these, so they're not going to be rich, but you could ask if they're infinitely many, and that is probably true and unsolved. So most problems of computing R are always very difficult. The only robust statement is the finiteness of R, and that's what I'm going to focus on. Yeah. Okay, so that was my first example. Now I'll give you another example. You might wonder what those coins are there. When I was writing about this, when I first started looking at this problem of Apollonian packings, I'm going to explain everything about this in a minute. I was looking for denominations which fit certain radii up to some multiple. And it turned out the quarter, nickel, and dime work perfectly. And you'll see the miracle. You can't start with any 4 circles, but you have to start with 4 circles which are like, there's going to be an analog of Pythagoras' theorem here. All right, so what is in this picture? There are 4 mutually tangent circles, and the 24 is 1 over the radius of this one, 21 is 1 over the radius of that, which I'll call the curvature, 1 over the radius. This is 1 over the radius of the external one, but the external one must come with an orientation, and it's got a minus in front of it. So there are 4 numbers there, minus 11, 21, 24, and 28. Before I do anything further, I'm going to do something with these circles. There's a beautiful theorem of Apollonius. Probably when Naiming and I took the qual exam at Stanford, this was one of the problems for tests if you understand the Mobius group in a second. Here's the theorem of Apollonius. Apollonius wrote many papers, many theorems about circles. Is if you have 3 mutually tangent circles, like these 3, there are exactly 2 other circles in the world which are mutually tangent to those 3. So we see one of them, that's the external one there. There's the other ones here, there's a unique circle that you can place in there which is tangent. And similarly, there's a unique circle you can place in here which is tangent, and similarly here. So let me do that. So I've now placed in these new ones. Now the thing you should be very shocked at is that the new circles have curvatures which are whole numbers. That's completely unexpected. Because you might do some geometric construction, you might expect there to be square roots or fractions, whole numbers. So that's because I started with 4 which were integers. So if the first 4 that I found satisfy some equation, then from here on out, every time I fill this in, I will get integers. And this is called an integral Apollonian packing. The fact that they're integers will become clear in a second. Actually, that was first pointed out by Soddy, a chemist who won a Nobel Prize in chemistry and was an amateur mathematician, this integrality. Okay, so we get a sequence of numbers here, all are integers. And this is going to be the orbit, and I'm going to try solve Diophantine equations, meaning try understand which integers I get there, or try understand which of these circles have prime curvature, or twin primes. You can ask every question in the setting, and that's a setting in which this theory applies, and it arises naturally in many problems, but I'm illustrating in the very concrete problems. So I now continue, and you can see this carries on forever, and you get these bigger and bigger numbers because the curvatures are getting bigger and bigger, the radii are getting smaller and smaller, but they're all whole numbers. All right, so we want to ask the questions for this. That's it. Now you see, you can try to look for primes in these very small circles. In this case, the parameterization of the first type that I gave in the Pythagorean does not exist, but the second type is very much there. And that is the 4 mutually tangent circles, their curvatures satisfy a quadratic equation, a cone, but in one more variable. So it's the next after Pythagoras, and it's due to Descartes. That is that there's a quadratic form. This is a quadratic form in x1, homogeneous in x1, x2, x3, x4. It's got signature, if you know what that is, 3-1, rather than the other one had signature 2-1. So this is the quadratic form. And then there are these transformations for involutions. An involution means if I square this, it's 1. And these involutions are exactly the transformations that you create by going from putting the new circles into the old circles. So if I start with 4 mutually tangent circles and I make the new 4 mutually tangent circles, if the first 4 were integers, everybody afterwards will be integers because these matrices and their inverses are whole numbers. That's why the surprise, I've just explained the surprise why you kept on getting integers. Okay, now that we get integers, we ask all the same questions about, for example, primes, or which numbers do you get there? So the group that you get that's generated by filling in those circles is called the Apollonian group. It's generated by S1, S2, S3, S4. And it's a subgroup of all the transformations which preserve the form which have integer entries. Now, there's exotic number theory and there's number theory. This is exotic, unlike the Pythagorean case, and this is why everything will require new tools. The reason it's exotic is that unlike the Apollonian group is not equal, so the group that you get is not all the transformations, and it's a very thin subset of all the transformations. In group theory, it's the statement that it's infinite index. So you get a very, very special set of transformations and not all the transformations. If you got all the transformations, you would be in the language of ordinary number theory, the subject that many of us cut our teeth on, Hilbert's problems and things like that, about solving quadratic equations over the integers, Hilbert's 11th problem. But here we have a thin group, so just this construction from geometry forced on us the fact that the group is deficient. And then which solutions you get is much more subtle, and which primes you get might be much more subtle. So the standard tools don't apply, and I'll say a word about that. And this was one of the motivations for the development of this theory. So I'm going to, doing okay, I think, for time. So the Apollonian packing, those circles that you get, are in orbit of this Apollonian group of the starting 4. So if the starting 4, x1, x2, x3, x4, satisfy the Descartes equation, so that's why I chose the number minus 11 and those other 3 numbers. If those 4 start off satisfying the equation, then all the guys you fill in will satisfy the equation. And the orbit is the set of solutions. The Apollonian, the packing is an orbit. And that's the setting in which we want to study all these problems. Okay, so it turns out that, and this is a theorem that I proved early on in the subject, and that is that there are infinitely many circles in any of those packings, all of which curvatures are prime. So that's like the Euclid statement in the setting. And I could even do what the twin prime here, different problem, obviously, does not satisfy, not held back by the usual difficulties. There are infinitely many pairs of circles in the packing, both of which the curvatures are prime. So the setting in which this theory that my colleagues and I developed, that I'll explain in a second, is called the affine sieve. It's an extension of the Brun sieve into the action by a group like this, acting on space, taking integers to integers, and then studying whether you can get primes or almost primes. So in the language of saturation, making one coordinate prime you can do on a rich set, and making product of 2 of them prime you can make on a rich set, and that's these 2 statements here. And this theory is really thriving. There are many, many developments, even the most recent by Haag, Kurta, Rickards, and Stang, 2023, where Stang and her collaborators showed that there are obstructions. So you might ask what integers appear in an integral Apollonian packing. It turns out that there are obvious divisibility obstructions, and it was believed that basically those are the only ones, and they showed that's not true by tremendous insight. So this is a thriving subject, and the Diophantine theory, the sieve theory is more or less complete, as I'll explain now. And then one more example before I state the theorem, and then say just a couple of words about what is difficult in this. What's so different to the ordinary setting? And this is a cubic equation. So I worked on quadratic equations for many years. Finally, I promoted myself to a cubic equation and got stuck immediately. This is already hard. So this is called Markov's equation. It comes up in many different contexts, at least 7 or 8 that I know of. So it's a fundamental equation, and we look at it over the integers. So this is sum of 3 squares minus 3 times the product still equal to 0. There's a solution x1, x2, x3 equals 1, each one. That satisfies this. And that point 1, 1, 1, actually one can get to all the integer solutions from 1, 1, 1 by a group of motions. So now I have transformations of 3 space to 3 space. Here they are. They also involutions. So I take x1, x2, x3 to, I don't change x2, x3, but I change x1 to 3x2 times x3 minus x1. And you can check by hand that if this, if your point satisfies this equation, so will this guy. If you apply R1 twice, I just get back to where I started. So these are involutions, but if I apply R1 and R2, I get a completely new transformation. And if you compose two nonlinear things, you get a bigger nonlinearity. So when you start to do this, it gets very complicated. But it's a theorem of Markov that all integer solutions to this equation are in one orbit, except 0. So these are the non-zero. I take 1, 1, 1, and by applying R1, R2, or 3 repeatedly, I'll get to every solution. So this is an orbit, and we set up now exactly where we can try to do a sieve and a Diophantine analysis. This is a case where we know very little, and which was the case for which this whole theory was invented, and we still don't have a complete answer in this case. But the Diophantine analysis reduces to an orbit. This action now is nonlinear. That's the main difference. All right. So if you excuse me for 2 slides, those are in high school, just listen to my body language. I want to just say a few words as to what the theorem is and then return and explain very concretely what the difficulties are. So the setting in which this work, and I'll say who it's by, is developed is I've set it up so I have an orbit. I have a point in Zn. I have transformations of space, polynomial maps of n space into itself. I want integers to go to integers. I'm only interested in integers. That I think has become clear in this lecture. And I look at the smallest set defined by polynomial equations, which contains this orbit. It's called the Zariski closure. So the integer points, by definition, are rich in that. And the orbit, since the orbit is, I'm taking X to be the Zariski closure, the orbit is rich inside there. So everybody's rich here. There are many solutions rich enough to be dense inside X in the sense that I've been talking about. And now I take a polynomial in n variables, and I define the saturation number just as I've defined throughout. And the big theorem is that saturation number is finite. So this is the main theorem. And only in the affine linear context do we have a complete theorem. So this is due to Bergan, Gumbert, and myself. We developed the basic theory. Gold, Seferdie, and myself proved the final version of this. In between there, the subject exploded into an industry with many, many authors. I won't repeat them here, whose work is used in doing, proving certain things are expanders. Anyway, the main theorem is that you can tell whether F, the saturation number, is finite by standard mathematics, by computing standard things, algebraic groups. So G is the Zariski closure of gamma. That's easy to compute these days. And as long as G is what's called Levy semi-simple, it's a necessary condition for our proof to work. It turns out that basically it's a sufficient condition. It's also necessary. So our theory is complete, meaning if you drop that condition, then saturation won't happen. And so this is a complete theorem. Then you'll always be able to execute a Brun sieve and show that the set of points in this orbit at which F has at most R prime factors is rich. It's a very general theorem. And of course, we try to follow Brun, but I'll explain in a second why it's so difficult. So this is a statement that this is a sharp theorem in the linear case. I was told I started at 22, and I have 3 more minutes. All right, the proof draws on many, many things, from representation theory to dynamics to number theory to algebraic geometry. That's sort of what you would expect. But I want to explain one point that's really, to me, the most interesting point here. Remember when I said in the Brun sieve, we can count how many numbers there are in an arithmetic progression using our fingers. It was t divided by q plus some small remainder. what changes in this example? We have this dynamics which is associated with the kind of moves that I was showing you in the Pythagorean case or the Apollonian case. And that is that if I look at a ball, so the sets look more like trees than like the line. And if I look at a ball radius r on a tree and I ask how many points are there in a ball radius r which satisfy some congruence, I need to be able to count that. To do this, what does the sieve do? You count the number and you remove the guys you're counting twice, you add in the ones you're counting 3 times, back and forth, and you truncate that process optimally so as to get meaningful upper and lower bounds. That's what the sieve is about. So if you try to do that, you need to be able to do this count. And there's a big change in the world that the number of points on the boundary of a ball on, say, a tree like this is the same as the number of points inside. Same order of magnitude. So in 2 dimensions, or in 1 dimension, if I look at an interval, the boundary of the interval is 2 points, and the interval is very long. T is going to get large. So the interval is long, the boundary is very small. In 2 dimensions, the boundary, the length of a circle, radius r, is 2 pi r, and the area is r squared. So the number of points inside is r squared, but the number on the boundary is much smaller. But in hyperbolic geometry, which is where this is taking place, the boundary is as big as the middle. And so a fundamental new issue comes up. And in the case that the group was not thin, the Ramanujan conjectures are what save you. So this was particularly pleasurable for us because originally we used number theory to make Ramanujan conjectures, as was mentioned, to make combinatorial objects that computer scientists wanted. And in a recent conference, for my 70th, Dan Spielman got up and said, the great gift from number theory to computer science was Ramanujan graphs. But they gave us a gift. So for many years, we were giving them something. They gave us tools to prove the condition to execute the sieve, how to show something is an expander without using fancy algebraic geometry, which is what we were using in the Ramanujan graph case. So this is the statement here. And this was particularly, we had to show that certain graphs associated with the setting are expanders, and you can't use the standard tools of number theory, and the tools are coming from information science and combinatorics. So when you marry 2 fields, usually the problem that's hard here is hard there, and you've made no progress. You just retranslate it into another language. But when you get lucky, the different view might offer something, and when it really starts to offer, both fields feed off information back and forth that can really enhance both fields, and that's what happened here. It just took much longer for the computer scientists to give us what we were looking for. Initially, we were giving them what they wanted. So this is a very general theory, and especially in the thin case where you can't use the standard fancy machinery, the Langlands program as it's called, you have to get by with much more basic things. When you're nonlinear, it's much, much harder. And the only progress that we have here is on that Markov. Again, Bogan was involved in this. We're still writing these series of papers. We have not been able to execute the sieve, but we have been able to decide what happens if you sieve and you strike out all the multiples of 2. You need to know what's left. So you need to know what's happening modulo 2. You need to know what's happening modulo 3. You need to know what's happening modulo any prime p. That's why primes are so important. So you need to know what's happening when you reduce the story modulo q. And doing that in the Markov case is incredibly hard. But we've been able to do that. William Chen added a very important contribution. And we know that if you now take the solutions to Markov equation and you reduce modulo p, you get all solutions modulo p, at least if p is large enough. This is the best we know at this point to executing that kind of mathematics that I'm talking about in the nonlinear case. This is wide open. Those who are young enough that you don't know what I'm talking about, you're the ones who are going to have to solve this. The nonlinear case is really the challenge. The linear case is what we were able to do. So I think that's all I have to say. Thank you very much, and thank you for listening. mind is very full.
So thank you, Peter, for the enlightening lecture. We'll now start the question and answer. Hello? Can you hear me? So we will now start the question and answer session. I encourage you to take advantage of this golden opportunity to ask your questions, as it is a unique chance for you to deepen our understanding. Please don't hesitate to share your Any questions? Yeah, please.
Thank you for your very enlightening talk. You've talked, especially at the end, you talked about how fruitful the collaboration across fields can be, where maths gave stuff to computer science gave stuff back to maths. What do you say to non-mathematicians when they tell you, do more useful things? Why are you focused on twin prime conjecture or whatever? That's not going to help me. Look at this other stuff you've done, which does help me. Why don't you do more of that?
Okay, I'll answer that. Can you hear me? Yeah, it works. This is really applied problem. Yeah. So, I mean, that's a very fair question. I don't think there's a difference between math and applied math and applications. We're all trying to solve hard problems. The main difference, and this is related to this question, is mathematicians who call themselves pure mathematicians do not do it with the applications in mind. That's not what's important. Of course, if you discover something new about numbers, like all crypto systems are based on being able to factor quickly, which, by the way, I believe you can factor quickly, but I don't know how to do it. But the issue there is very practical. It's a question about prime numbers. So if you discover something true, deep about geometry, which is or topology, which is about the shape of things, or analysis, which is about studying usually partial differential equations or something, or combinatorics or number theory, that will be used because that's the language of modern pretty much everything that's used quantitatively. So we try to understand the truths. We're not motivated by the applications, but of course, if there are applications, I'm always listening, and I will always try improve what we're doing if that helps in the application. But the only difference is we are motivated by what we believe are the fundamental truths. We're after the truths about mathematics. And I think that's a good answer, and time has proved over and over again that mathematicians seem to have good taste because it may be that that's all we're feeding the world, and you're going to use what we feed you. No, I don't think so. But I mean, if you think of Riemann inventing the Riemann curvature tensor, and then Einstein needing that in order to write down the Einstein equations, where Riemann was doing this purely as generalizing Gauss's notion of curvature, you see that at least Riemann had great taste. We like to think that we know where the real truths are, and when I was talking about twin primes, it's a problem that is compelling. It's not fundamental that any of us know, but the tools are. These sieve methods are used to make quantum gates optimally, things like that. So I think the answer is we're trying to understand the truths, and we are very excited if it's used. On the other hand, number theory never used to be at the forefront of this. Gauss, who invents pretty much everything, starting with curvature, Gauss, well known to have said, number theory is a queen of mathematics, and it's not really going to be used. Hardy was very proud, if you read his mathematician's apology. So he was an analyst and number theorist. He's very proud that mathematics, he was very disturbed that math was used to make weapons and things like that, and number theory would never be used. It's the pure, how wrong he was. There's nothing more applied in the digital world than parts of number theory. So I think I don't know if we have good taste, but at least I think there are problems that drive us which have proven to be the right ones. Of course, there's the frightening thing that some problems that we look at are not decidable. And there are problems that sort of become so important because you see everything else would fall apart if they were not true. So I think the answer is that we do contribute to the applications.
Further questions? Yes, please. Zhang Xin. Yeah.
So, are there infinitely many primes in the Markov triples?
Yeah. So
Experiment.
Mersenne primes, we also don't know if they're infinitely many, and that's why it was quite remarkable that this fellow found such a big one. The sieve methods that I've been telling you about, I said it's very robust. So even the saturation is, we don't know there. Never mind infinitely many Markov primes, which is a fundamental question that was asked very early on. So in this elaborate inclusion-exclusion, you need to have the number of points you're counting to grow faster. So if you're doing some kind of counting and the number of objects you're counting up to x must grow like x to a small power in order to any of Brun's sieve methods to have any chance of ever working. So when the sequence is very lacunary, there are very few solutions. So the thing about Markov's equation and Markov numbers, the number of Markov numbers less than x grows like log x squared. It's very sparse. By the way, one can prove that Markov equation is so central that the best way to prove that, and the way we use it when we apply it to do some elementary sieving, is we use Mirzakhani's work on dynamics, Teichmuller dynamics, which is how we count the number of solutions in our work. So it's very sparse, and because of that, saturation is not clear, and I'm pretty sure it's false, and I can explain to you why. So the Markov being sparse makes life very difficult. Are there infinitely many Markov primes? Of course. But by the way, I shouldn't say of course. It's a purely, you model it and you say, by random considerations, I would expect there to be infinitely many. So maybe I shouldn't be saying that. But that's really infinitely, everything's infinite, infinitely harder than twin primes. Twin primes, it's frustrating that we can't do.
Yeah.
Further questions? Yes, please.
Can you advise those who think their talent is not enough to get into pure mathematics field?
Firstly, don't underestimate your talent if you're talking about yourself. The main thing with pure math is, do you like the subject?
Yeah.
If you like the subject, I'm sure you've got the talent. Sometimes pure math's a big field. People have talents in different directions. Understanding pure math will allow you to do anything else as well. So I'm not sure I agree that pure math, the way you're talking, it sounds like you're saying pure math's harder than other math.
No.
No, you're not saying that.
But it is kind of abstract and...
yeah, the abstraction is what makes it beautiful. Exactly what makes it clean. You know, you take all the problems I talk about are concrete. I've always only concentrated on concrete problems. But to me, what changed me, I used to be a chess player, essentially professional chess player. What made me change to math was the minute I saw abstract math. I saw that this is you take a problem and you think about it more abstractly. You don't think about the exact concrete problem. You put it in some setting, and then the truth emerges much more easily. You just need to get used to it.
Thank you.
Yeah, so the first question from...
Hi, Professor Sarnak. Thank you very much, and I enjoyed your talk very much. So I'm just a secondary school student, so I don't fully understand the entire presentation.
Yeah, most lectures, the lecturer doesn't understand it either, yeah.
But like I have some background in Math Olympiad, and so in Math Olympiad, number theory and geometry are two very important stems. But in most of the questions, they are not related at all. And I think geometry is being seen as most Olympiaders that geometry is very detached from the rest of the world of mathematics. Say the closest connection that we see is mostly often like combinatorial geometry. And so I was a bit surprised that there was a talk that links between number theory and geometry, these two seemingly unrelated topics. And so actually, from what I understand, it's kind of like from what you have just said, it's like you have some quite specific geometry, and you wish to like decrypt the conditions, and after that it becomes a purely number theoretical problem. And so what do you think is the intricacies or the importance of the connection between these two seemingly unrelated fields? Thank you very much.
Yeah, I think it's a very good question, and I think the mixture here is a bit surprising, but I think you deciphered it correctly, that once you convert it to this orbit and group theory, the geometry is gone. That's exactly right. Doing this in general, groups come everywhere. And groups don't always come. Okay, so the group that appears here, there were two groups. There was OFZ, that was all matrices which preserve the form. And that's defined globally. I look at all matrices with this property. And then you are in the realm of very standard but very advanced math, algebraic groups, discrete subgroups, arithmetic groups. But groups that come like from this Apollonian packing or from monodromy or from many, many problems are born with generators. So you saw I had 4 transformations which generated the group.
Yeah.
And then when you do that, you usually get something that is called thin, what I'm calling thin. And so what's going on here is that those are everywhere. That's the typical thing. And all the standard tools then just drop down. And so the significance is that in all those problems where the group is defined by the geometry dictating who the generators are, something called monodromy, where the generators are coming from certain cycles, then when you ask this kind of question, you can now answer it. So I think, but you did decipher something very cleanly there, and that is that you first transform it, yes, into groups and things about groups, and the geometry is then gone. In fact, the final setup didn't have geometry, it just had the groups. And as far as Math Olympiad, yeah, I'm glad to, I've always said that I've had many students who've won many competitions, and some of my colleagues say that's not good. And I've always said the opposite. That means they're very talented, and it's a good thing. Just I need to guide them to use their talent and not just to solve math competition problems. So, yeah, it's a very good talent to have.
Yeah, please.
Hi, first I want to say thank you very much for the talk. It's quite interesting, though I didn't understand some of it, of course. But honestly, I first came here to the lecture because I have a sort of hobbyish interest in mathematics. It's a bit interesting to me. But I was surprised to find that a lot of the terms in the lecture I'd actually already studied from some of my computer science courses. I studied computer science. So now I'm quite interested in like the overlap between sort of algorithmic computer science and pure mathematics. I'm wondering if I wanted to look more into this field, are there any recommendations, what I should study, or like, yeah, just stuff like that. Thank you.
Yeah, so I can answer that, should I? Yeah. Yeah, so the part of, so computer science and math are very closely linked, but the part that's very closely linked is analysis of algorithms, complexity theory. And that's essentially mathematics. You're trying to understand the speed in which, so mathematicians try to solve problems, try to understand what problems you can solve. And in complexity theory and computer science, you ask how quickly you can solve something. And that part of mathematics is even represented in the International Math Congress as a part of math. I think it's recognized there as much as anywhere else. And that's where the connection is the greatest, where the tools from counting, so it's very close to combinatorics usually because you're trying to understand how quickly an algorithm runs. The tools that I was talking about, the connection that I'm talking about, is where you're trying to construct some network which has, so this is a Ramanujan graph, it's a network which is extremely sparse but also very connected. That's what these expanders are. And those are very hard, so you might see they exist by showing the random guy has a property, but to make something explicit could be extremely difficult. And somehow number theory, if you can't solve a problem with a formula, then usually what we're trying to do is show that something's random. And that's why it's hard, because we were trying to show something explicit is random, and something explicit can't really be really random. So this connection is why it feeds off so well. The books that you should read, I think, are on complexity, but in terms of expanders, there's a very beautiful article of 100 pages by Vigdison, Lineal, and Huri on the applications of expanders in theoretical computer science. And it's a very well-written paper, and I highly recommend it. It explains how to use it in coding theory. Yeah.
So someone has the mic. The last question, please. Yeah, at the back. Yeah.
Me?
Yeah, please.
There's this young guy here.
Oh, okay.
So, like, I really enjoyed the presentation, first of all, and secondly, like, when you did your bachelor's in Witwatersrand, if I'm not wrong, and eventually your career progressed and you were part of the academia for a long time. Like, throughout this time, have you ever felt like that a particular topic is not for you, or you felt like changing, like switching to something else? Or how did you decide like number theory and geometry is your niche? Like, how did you like navigate pure maths? Because like there are so many stems and stuff. Like, what made you think that no, I'm pretty sure curiosity was a huge driving factor, but like, what made you like feel that no, this is it? Because I'm pretty sure a mind like yours might be curious for a lot of stems in pure maths.
Please.
Yeah. So I think I'm maybe the mathematicians with different styles. Some stick to one field for always and develop it very, very far. I'm, as you can see, interested in different areas, but you find at some point you start thinking about the problem and you keep on generating the same set of ideas. And the one thing that I found that I like is, all right, it's clearly I've kind of saturated that for the while, but you must never forget what you've done, because then you move on. You have to become an expert at something firstly, so that you have some base. And as you start to look around and find interesting problems, you learn the new field. I believe in problems, not in fields. Problems, and then you learn whatever you need to learn to try to study them. So you've got to find that it's a compelling problem and an interesting problem. And if you stay in academia for a long time, I find that it's a good idea to move around, but never to forget what you did, because often you start thinking about something else, and then you realize, wait, that's exactly what I needed when I was trying to do that. So you don't forget what you've done. You've built this intuition, but there are very different styles, and my style is very much broader, and I enjoy that. And I like to see what other people are doing also.
Okay. So I saw someone on the second row. You were raising a question. Very, very quickly. Yeah, please.
So for the sieve, I want to know if like after an infinite terms of numbers, will the generalization of sieve be broken? The method.
So I'm not sure I understand the question. If you go to higher dimensions, which is what is that what you meant?
Yes.
So that's what our big theorem is, that if you do it with an orbit, you will be able to execute a sieve unless there's some conditions that I didn't tell you about when this fundamental theorem will not apply. So in going to higher dimensions, if you're just looking at Euclidean space, it would be the same. But if you move to hyperbolic space, which is what these other groups are, then you got to be careful, and sometimes it's true and sometimes it's not, and we've understood it.
Thank you.
Okay, so the question and answer period has to come to an end. So thank you very much for your interesting questions. Thank Professor Peter Sarnak for enlightening us.
And let me thank you all for coming.
May I now ask you to stay for the souvenir presentation? Professor Han, please.